Well, the first day was about the products. And then we decided, as you're seeing, that we would start to talk about the regions themselves. And someone with a certain obsessive compulsive disorder might want to do all of the theory and then all of the observations, or the other way around. But we thought it would be more fun to weave them together. So that's what we're going to do. And I hope you have fun with it. I think we're going to have fun with it, going back and forth between the two. So I'm going to tell you the story of not just a star-forming region, but I will be honest here, my favorite star-forming region. So this lecture is actually about a region that I've come to know very well and has started to attract a lot of attention. And then tomorrow I'll talk about some more classic regions. The region is the Lambda Orionis association. Lambda Orionis is the brightest star in the head of Orion. That said, it's not a very bright star, which often leads to jokes about Orion's wisdom or intelligence. Usually you can hardly see the head is there with the naked eye. It also is the source of one of the most spectacular shells in the IRAS 100 micron maps. And it also, maybe you could close the blinds just a little bit because there's a lot of pretty pictures here. It also is the source of a particularly beautiful H2 region, a sharpless region, that is driven by Lambda Ori itself. So there's a lot going on here, and what makes it a special region compared to many is that, as I'll say at the end, by conjecture, a supernova has gone off here and essentially cleared the region. So what you're really looking at here, and I guess in a sense I'm working backwards in time, you're looking at a star-forming region that has just now been exposed. It's just cleared out, not completely as you'll see, but certainly around Lambda Ori itself. And so we can actually do a very direct census of what's there and how the region evolved. So let me begin. Just to give you a sense of where we're talking about, and I'll also use this slide tomorrow as well, this is the galactic plane. This is the Orion molecular cloud here. Taurus Auriga, which of course is very important to us, actually on the scale of this, looks like you wouldn't pick it out necessarily, but Taurus Auriga is up here. This is the Orion Nebula region, which of course is very hot and bright at 100 microns. This is sort of what one typically thinks of as the cloud, and the region that we're going to be talking about is right up here. And this whole region, of course, was a large OB association that was mapped by Adrian Blau. And more recently, we've come to know about young embedded star clusters in the region. So in a sense, for the next 2 lectures, we're going to be talking about this entire region. That's where we're going to be focusing. But for this lecture, we're going to focus here.
Is this shell visible? Is this the supernova? Or?
I will suggest that it is the shell driven by a supernova. There's never been a pulsar detected or any real evidence for it. That's not a supernova shell. This is 100 microns, so that's a dust shell. So we'll start really with the census of actually I'm going to start very briefly about the dust and gas, the massive stars, the solar type and the lower mass stars. I'm actually not going to talk about outflows. And then the story of the region. So to begin, just as an overview of everything that we have here, we have Lambda Orionis itself, which is an 083 star, so it's probably of order 10 to 15 solar mass star. It actually is a binary, a 4.4 arcsecond binary, with a lower mass star of B05, which is not a star to be ignored in this story. And then there are 10 other OB stars in the region, in the entire region. There's about 6 or 7 right in this very characteristic clump here, this very dense clump of OB stars. There's an H2 region, which I showed you in the previous picture, that's ionization bounded. That's driven by Lambda Orionis itself. There's a 60 parsec ring, so that's a scale to keep in mind here. This is about 60 parsecs across. Of neutral, there's actually an H1. The very first thing that was discovered, well, was probably the H2 region. And then in the 50s, there was an H1 ring that was discovered outside of this molecular ring. And there's quite a few Barnard dark clouds, which I'll show you in a moment. There are solar type and low mass stars along with the OB stars. There are classical T Tauri stars, which is nomenclature for stars that still have disks. And there are weak-line T-Tauri stars nomenclature for pre-main sequence stars, young stars. Both of these are pre-main sequence, but less evidence for disks, certainly less accretion going on. And then just for those of you in the field, but you might not realize that FU Orionis is part of this system. This, of course, is the namesake of the FU Orionis effect in star formation. And there's quite a few Herbig-Haro objects. There's a lot of jets in this region. So there's a lot of action still going on. Obviously not around lambda Orionis itself because there's no gas there, but in the ring. So these are the Barnard clouds, the extinction clouds. And you can see that they map very well onto that ring. There's so many different ways that you can show the ring. But these, of course, have been known since 1910, 1915 by Barnard himself. Then there's the IRAS 100 micron emission, which I showed you as a sort of a image, as a picture, but this is the contour plot. And associated with that, as Kathy mentioned this morning, is usually the case, is CO emission. So this is molecular gas emission, presumably associated with H2, that is to say molecular hydrogen. And if you actually compare the IRAS, let's see which, this is, going to get this right here. This is the IRAS, this is the CO. You can see the close associations with the more extensive emission relative to the more extensive CO. Most of the dust does not particularly have a heating source in it other than the central star. So the brightness in the IRAS is truly a measure of amount of a dust. So that's the sort of the broad scale domain that we have here. There's two very famous clouds that you'll see why shortly, B35 and B30. For again, those of you, in the field, I'm just trying to associate that you may have been working here before you even knew you were in the lambda Ori region. Many, many, many people study B35 because there's a lot of action going on in there. The total molecular mass in the ring now is about 10 to the 4 solar masses. And there's been suggestions that the ring is actually expanding. My own sense is that that really has not been definitively established. It's not that important for my story. This is important. And that's, of course, a lower limit on how much gas was there when all of this started. But essentially, we're talking about a small giant molecular cloud here. Okay, so now the more classical side of this, if we actually do some Strongand photometry, as Chris Dolan did, and put the OB stars onto a color magnitude diagram, and basically the reason I'm going through this is I want to show you how you do a full census of a region. These, of course, are only the OB stars. There's some fairly evident non-members. A dark circle is one that's in this clump here, right smack in the center of the region. An open circle are other B stars that happen to be around the region. But you can see that there's a pretty good main sequence here, especially if you allow for binaries. Lambda Ori itself is somewhat evolved, and another star is also a bit evolved, and the rest of it lays on the main sequence. And photometrically, you can tell some which aren't members, CMD non-members. So at the massive end, you've got a pretty good census of what this region has formed. And you notice that I'm avoiding so far the phrase OB association, because I think that's anachronistic, as I'll show you soon. Now, the reason OB associations were first discovered is because the OB stars are easy to see. The reason I think it's anachronistic is because they're just the top end of the IMF. But you have to find the rest of the IMF. So I'm going to show you different ways that we can find low-mass stars in star-forming regions. And I want to point out, I didn't just put this here sort of because out of interest, that there's a lot of legacy in this subject, right? Haro and Herbig started this back in the 50s with objective prism surveys looking for H-alpha stars, H-alpha strong stars, and in so doing really started this field that we're still talking about today. These objective prism surveys were done a bit more systemically by Charlie Lotta and his students in 1982. They surveyed the entire region with an objective prism survey. And these circles, these dark circles that they found here, are strong H-alpha emitting stars. In other words, within our current paradigm, These are young stars that are actively accreting, presumably from disks. And what Charlie noticed, and this was in the era when giant molecular clouds were really first being discovered in the millimeter, was that even though they surveyed this entire region, they only found classical T Tauri stars in what was a relatively linear domain here from B35 to B30. And right around this time, people were noticing the giant molecular clouds also tended to be very elongated. And about this scale and size, this is about 50 parsecs. And so Charlie surmised that what we really were looking at here was a fossil giant molecular cloud, within which this group of OB stars had formed in really what is a very tight cluster. And I forget whether Charlie surmised the supernova or not. That's neither here nor there. Something obviously has cleared the region out. Okay.
Sorry,
Please.
just a question. I mean, it's detailed really, but I think in this region, in Lambda, there's a cluster that is called Colinder 69. Where is it?
The reason I'm smiling is because we have all been working on this region for about 20 years now. And about 3 years ago, someone noticed that the cluster here is Colinder 69. So now, the reason I'm laughing, I only discovered that about a week ago when I looked at one of David Barrado's papers, and now he's calling it Colinder 69.
Yeah, that's why I wanted to know exactly if it was.
It's this cluster right here, which I thought I had discovered. Hey. That's another thing about this field. You find that no matter what idea you had, George Herbig had it 40 years ago. Please.
What's the mass of the cluster?
Well, we're not there yet.
Okay.
Not very, actually, to answer your question. So it's a few hundred. I'll just point out that the vast majority of the stars that they found as H-alpha stars were also the variable stars in the region, which is quite common. So variability is another way to search for these stars, although it hasn't actually been done in this region. The approach that we pioneered was really based on the advent of multi-object spectrographs. The ability, in our case, we thought 100 was a lot. To do 100 stars at a time, of course, now doing 300 is quite common. And the beauty of young stars, let me back up. The problem with H-alpha is that you only find the classical T Tauri stars, the ones that are actively accreting. And we know that, in fact, the population has many non-active accreting stars. How do you find them in a systemic way? X-rays is one way. ROSAT didn't really go deep enough to go very deep for that purpose. I'm going to show you a set of other ways, which will ultimately include XMM Newton. X-rays are very, very useful. But about this time, I had just been thinking the one thing that is characteristic of all low-mass stars is that they have strong lithium absorption lines, because lithium is not burnt in pre-main sequence stars until they get much closer to the main sequence. I won't go into the interior structure, but the point is the lithium line at 6707 is a diagnostic of youth. And so if you can take spectra of a whole lot of stars in the region and pull out the ones that are lithium, add to that the kinematic criteria that we've already been talking about, you should be able to do an unbiased survey for low-mass stars in the region. Just to give you a sense of scale, we started this idea when the Wind Hydra multi-object spectrograph came online. We had a 1 degree diameter field, which at the time was a lot, but of course we're talking about a very, very large region here. This took about 10 nights, 4,000 spectra, 3,600 stars. About, whether you want to work in angstroms or nanometers, 40 nanometers. We worked, I'm telling you this because you may want to do this. It's a very effective technique. We worked at 664 nanometers, which gets you both H-alpha and 6707 lithium and a rich array of lines for measuring good radial velocities. This is a very good region to work at for this discovery approach. You need a spectrograph around R equals 20,000. That's a spectral resolution of about 15 kilometers per second or so. Very typical. These days, this is very typical instrumentation. And you need a signal to noise to get down to 0.1 angstroms in equivalent width. None of this is hard. The hard part's the multi-object spectrograph. Once you've got that, the rest of this is very straightforward. And we had a RV precision of about 0.5 kilometer per second. But here's the bottom line. This is a plot of lithium equivalent width versus radial velocity for an entire unbiased population of stars in 1 degree fields within the region. And you can see the separation. I mean, it's just a beautiful approach. Essentially, anything above 2/10 of an equivalent width, you can come at it either way, they're both gorgeous, right? You come at it kinematically, here's the cluster, right? I mean, there's the association. I shouldn't say a cluster. And this is also the Orion velocity, so it was no surprise. You come at it from this direction, here's the strong lithium stars. You put them together and you've got an extremely clean membership approach. And of course, in addition, just you get binaries for free, which is a wonderful thing.
Bob, is this a sample drawn from everything that sits above the main sequence projected to the distance of Orion?
Yes, which I'll show you in just a second. So we did not literally do every star because some stars clearly couldn't have been pre-main sequence at that distance. So these were the fields that we took. And the main thing that I want to point out is, of course, we were working along Charlie's linear domain here. We'll come back over here shortly thereafter. The point is that, yes, Colander 69 exists. Earlier studies, which is why it caught me by surprise, there's quite a few studies in the literature that really only find the OB stars. They don't find any low mass companions. And frankly, if you look at the sky survey, it's not obvious that there's a cluster there. So I need to go, he's dead, but I'll go check out his papers to see how he found it. But clearly we found, if I remember, of order 70 or 80 low mass pre-main sequence stars associated with the OB association. And then we also filled in the region in between and showed that there was a large domain, a large low mass population in this region. So if you want, it's an OB association with a very tight clump of OB stars and a much broader low mass association. Now, if you want, in the old days, you would have said this was a T association, that's a T association, here's an OB association. You would make these sort of post facto analyses of different regions, which is why when you asked me the question, are most stars made in OB associations or otherwise, I stumbled around because it's an old question, right? The question now is that clearly both populations fall within the fundamental unit of the giant molecular cloud, and the question becomes, where in the cloud do different types of stars form? And that's what we're going to be talking about in this region. And how does the global productivity of the cloud populate the field? Please.
What's your completeness?
Down to roughly 8/10 of a solar mass, I would argue we are 100% complete.
Okay.
But now I'll show you that there's a lot of low mass stars that we haven't touched because of brightness limits.
Okay.
I'll show you that in just a sec. Okay. Please.
Is there a lot of extinction going on, or why does this look like a filament and there are no stars around?
Well, that's why this is such a gorgeous region, because this has all been cleared out by whatever it was. I think it was a supernova. The extinction to these stars is very, very low. The extinction within these two clouds, B30 and B35, can be quite high. In fact, there's some embedded sources within these clouds. But within this region, you got a snapshot. Literally, I think it was cleared out about 1 million years ago, and the extinction is very, very low.
Yeah, my question was actually how long it would have taken for that to clear out. If you know the distance, you probably figure that out.
It's about 1 million. It's about 1 million years. I'm going to come back to that, but the question was not so much the age of the system. I'm going to tell you soon that this system began to form about 6 million years ago, but it was cleared out about 1 million years ago. In other words, it was revealed 1 million years ago. Deep photometry is another way of finding low mass stars. This was Michael's point. If you go very deep in this region, this is the field. This is the ZAMs at lambda Ori. And so all of these stars are candidate pre-main sequence members. To actually prove that they're pre-main sequence, you've got to get some youth diagnostic. Lithium is a good one, although these are getting very faint. This is essentially where our study stopped. This is where the Barado study picked up with deep photometry, only right in the core, only right around the OB stars. But it's another way to find low mass stars. There's a pretty good separation from the field to the pre-main sequence. We did a similar study, but not as deep, by doing imaging over this entire domain. This is why you have thesis students, because there were a lot of CCD images taken here. And the main result, I won't go into it in great detail, but the densities between these two clouds is clearly higher than it is out here or out here. In other words, there aren't, even though we didn't come out here and look for lithium, because there were no H-alpha stars out here, there were no tracers of formation. In fact, this region out here is not highly populated with young stars. I won't go into the details, but there's a certain level of contamination going on in here that's consistent with the only density, overdensities being along this line here. Okay. And then finally, the X-rays. I mean, X-rays are incredibly valuable for searches because young stars tend to have very, very active chromospheres, much more active than the main sequence, and that's what makes X-rays a diagnostic. It's kind of a surprise that such a high energy phenomena would be a diagnostic for what is usually considered to be a low energy cool event. But they're very effective. For our original study, the Rosette observations are mostly confirmations of stars that had already been found by other techniques. But with XM Newton, we can go quite a bit lower, and this will be relevant later, but this is, you know, I noticed that in the paper they don't have masses here. It's kind of amusing, actually. But our detections were from here on up, and of course the OB stars are out there. And then this is the XMM detections. And these are the non-X-ray detections in the Barado photometric sample. Okay?
That happens if Radial crashes when using multiplot and you don't reset it afterwards.
Is that how that happens? I still do things on graph paper, so that's not a problem. So the reason I'm going through this is because I'm not going to do it for every other region, but the point is you use multiple techniques, some new, some not so new, some reaching back to data from 50 years ago, to triangulate on the membership of a region. And you'll notice the one that I really haven't used yet is infrared imaging, mainly because the region itself has already been exposed. So I'm just reminding you that we have a full population in this star-forming region of things that are characteristic of star-forming regions. We've got OB stars, we have solar-type stars, some co-spatial with the OB, some located elsewhere. We've got extinction clouds, we've got H2. There's a lot going on in this region. Okay, so that's the census side of it. Now, how do we actually analyze these things? The first point I'll just make, for clarity if you're interested, it turns out the photometric distance, essentially mean sequence fitting, is comparable to the Orion molecular cloud. So everything hangs together pretty well for this being part of the Orion molecular cloud. It's a little far away for Hipparcos, but Gaia will nail it. And of course, what I really want from Gaia is to know what the velocities of those OB stars are, for reasons that I'll show you in a minute. So these are the issues that one typically might extract from a star-forming region. So very briefly, I'm going to apply these to this region to show you how it all plays together. The spatial distribution we've already talked about a bit, but an important point is that the OB stars have a dispersion of 2 kilometers per second, a velocity dispersion of 2 kilometers per second. The radius of this little clump in here is only about 2 parsecs. So they couldn't have been unbound less than how long ago, based on this morning's lecture? 1 million years? We got a 2 million years? Okay. Remember, 1 kilometer per second is 1 parsec in a million years. So indeed, essentially, we have a handle on the dispersion, the velocity dispersion of these stars in this region. It is about 2 kilometers per second in one dimension, actually in 2 dimensions. And so if this thing were unbound less than roughly a million years ago, this clump would no longer be together. The closeness of this clump, the proximity of this clump, is a really important clue to the evolution of the system, because there is no mass there right now other than the stars, and they're nowhere near able to bind the system.
A question related to the
Yeah.
velocity dispersion. So was this done with the Hydra spectrograph?
Yes, on the low mass stars.
Oh, okay, because I was going to say for the OB stars, this would be tough to get.
Exactly, as I was saying the other day, so you were listening so very well, and I appreciate that. We do have Hipparcos velocities for the brighter stars. They aren't very good, but they're consistent with 2 kilometers per second or so. Pardon me?
Shouldn't they be lower?
You mean in terms of mass segregation? Energy acquisition. The Hipparcos data are nowhere near accurate and precise enough to be able to make that distinction. So the smallness of the OB stars gives us a very important clue to sort of their history. As I've already pointed out, we have this linear distribution of the lower mass stars. They aren't distributed throughout the ring, which implies that the ring was made post facto. We also have surface density enhancements of the low mass stars at B35. Well, here's B30 and at B35. I know it's hard to see in the back, but there's a whole clump of stars right here, plus several embedded sources. And there's a whole clump of lithium stars here as well, not as many embedded sources. So we have surface density enhancements of those 2 clouds and ongoing star formation in B35. And as I pointed out before, the spatial distribution looks very much like a small giant molecular cloud.
Is it clear that these velocities, they are unbound?
Well, unless Collender 69, unless Collender found a lot more stars than we found, yes. It's
Total mass, sorry?
Pardon me?
What was your total mass?
Total mass is about 150, 200 solar masses. And a velocity dispersion of 2 kilometers per second. You can compare that to an open cluster. I mean, just as a classic comparison, an open cluster like 188 has an internal dispersion of about 0.4 kilometers per second and about 1,000 solar masses on the same core radius. So, the IMF is interesting in several important ways. This is from Barrado et al. They followed the Reed rule and fit 2 power laws to the data. That's neither here nor there. This is plotted in the log compared to the Pleiades from Dr. Moreau. And you know, broadly speaking, there's a reasonably good comparison of this region, of the IMF of the region with respect to the field. But if you look with a little more detail, a little more care, you find something that really I consider quite important, at least. There's roughly 107 stars globally throughout the region between a mass of about 0.4 and 0.9. So you can tie that to different IMFs. We happen to use these 2, and predict how many OB stars that you would expect to find. And the answer is roughly around 16 or so. I'm sorry, around 10 or 19. We actually observe 16 in total. So globally, the scale of the OB stars is about right. But interestingly, locally, in the vicinity of lambda Orionis itself, where the OB stars are, we're down by roughly a factor of 2, which is why your completeness question was so important. Within this mass range, we're down by a factor of 2 over what we would expect, whereas away from lambda Orionis in the B30 and B35 regime, we're up by about roughly a factor of 3. So you put those 2 things together, and the point is that globally you get an IMF out of this region, but locally there appear to be variations. And in particular, in the immediate vicinity of the OB stars, it's not at all obvious that there are enough low mass stars there to be consistent with the field. Which is essentially all this says. So but I consider that to be fairly important.
May this
Please.
be an evolution effect? You know, for example, you could have more low mass stars in the center, and then they would just spread around.
So what you have to do is, this comes back to the timescale question. If they were released roughly 1 megayear ago, you have to ask yourself, how far could they go? And actually, then you have to do a census over a region that's large enough to take care of any possible expansion, which is exactly what we did. So that's right. I mean, that's good. Please.
You say that a star cluster has a field star IMF, essentially. Is one star forming event leads to a field star IMF? Well, I'm confused because in star-forming regions, there's supposed to be a saltpeter IMF with a slope of 2.35. But the Cooper-Towns and Gilmore IMF has 2.7, and this Miller and Scala is also very steep. How does that come?
I will allow you to reanalyze our data with whatever IMF you would like. Those were the 2 that we used. So I mean, if you don't like the IMF, which is quite fine, try it with a different one. Yeah. You have to appreciate that, well, I'm not going to go there. IMFs change over the years. And I realize that what you say right now is the IMF with a capital T and a capital I. But we shall see. Please.
At this point, I'm really curious about the ages. I want to know.
Oh, we're going to get there. Promise. So you've been asking about total senses. This is roughly the total mass in the system greater than 0.1 solar masses that is known at the moment. I say that because we didn't go down that low, only Barrado did, and he only did that in Colander 69, if you wish. The total cloud mass is about 10 to the fourth. So even if this changes by factors of 2 or so, this is the broad point that Kathy was making before. The global star formation efficiency in this region is, again, very, very low. But that's global. We don't know what it is locally around the OB association, what that core, what the mass of that core was. But this is a common result, which is why I'm putting it up here. The study of almost every cloud comes up with these kinds of star formation efficiencies. This is a bit of an aside, but I think it's kind of an exciting aside, and then we'll get to the story. We got H alpha for free in all of our spectra. This is a plot of, essentially, if you just draw a line across that linear distribution that I was talking about, this is a plot of H alpha strength. So this is B35 right here. These are the stars around B35. These are the stars around B30. And the thing that was most interesting to us is that there was a marked lack of H alpha emission from the stars around the OB association itself. Even though, as I'll show you soon, the ages of these stars are not demonstrably different. And the numbers are not substantially different either. The point being, and Charlie noticed this too, there are very, very few H alpha stars in the actual vicinity of the OB association. That suggests, at least it suggested to us, I think we were wrong, but it suggested to us that in that region, the radiation fields from the OB stars had actually affected the disks of the stars in that region. Whether it literally removed the disks or simply affected their accretion rates, I can't tell with it, because all I have is H alpha, and I'll show you the new data now. But what everyone agrees on is that the presence of disks around the OB association itself is substantially down from what you find around B30 or B35 or B30.
Well, that's not an issue with variable nebular background, is it?
Here?
The fact that you have spectra and you're trying to extract H alpha.
Oh, no.
H alpha in the background.
No, the surface density of the H alpha emission, we can't even see it. Our sky fibers don't have it. Yeah, maybe just a little tiny blip. Nothing compared to a classical T-Tauri equivalent width. So the point is that the frequency of accretion in solar-type stars is still very active around the clouds, and that the accretion frequency in the vicinity of the OB stars is not. And I'll show you shortly. We're going to get to ages in the next slide. But I will show you these new data from, in this case, from Hernandez et al., Noria and Lee Hartman and the like were working in this group. These are Spitzer data of stars in Colander 69 in the lambda Orionis region. And interestingly, the frequency of disks seems to rise as you get to smaller stars. There's definitely a deficiency. Remember, we were up here. And there's definitely a deficiency in disks among these stars. And David finds the same thing here. These are the XMM Newton detections. These are the Spitzer data for those detections. Again, both of these are right smack at the OB stars. You can see the lack of disks, but they too didn't quite get here. So whether or not the OB star luminosities are affecting disks in a way that's differential with mass, or whether this is an evolutionary effect at 5 million years, is not obvious, I would say, right now. This paper suggests it's an evolutionary effect, that we're starting to see the disks disappearing among those solar-type stars, but not yet among the low-mass stars. David has a slightly different interpretation. It's up in the air, is the point.
Sorry, Bob, are you suggesting that maybe it can just be interpreted that the more massive stars are co-located with the OB stars, and that's why they're lower?
Here, you mean? No, all of these stars are co-located with the OB stars. What they're suggesting is that what we're actually seeing here is an evolutionary effect that has nothing to do with the OB stars, but only with the age of the system. I'm honestly, I'll go as far as that.
Can you make the same plot for the whole region? In other words, out, away from the OB star?
To the best of my knowledge, it hasn't been done yet. There's no reason why it couldn't be. Oh, I mean, there is a reason. You have to get the Spitzer time, but yeah. All right, the age distribution. The reason we really went at this originally was we wanted to see whether there was any evidence for essentially sequential star formation. In other words, that supernova went off, is that what made B30 and B35 start to make stars? And I apologize, these are, and you're going to love this, because these are 3 different stellar evolution models from a decade ago, so you'll probably not like them either. But nonetheless, we did use 3 different stellar evolution models to look for distributions, age distributions around the dark clouds as compared to around the OB stars. Let me pick one that's probably the easiest for you to see. Now, I'll go with this one. This is log age. This is 1 megayear. This is 10 megayear. Okay, just to give you a sense. And this is, I think that's 0.1 megayear. Down here, of course, no, you wouldn't believe the age is too much, which is why that might be 0.5. But by scaling, it looks like 0.1. These are the ages. Remember, 2 of the OB stars had evolved, so we can get evolutionary ages for them. The OB stars formed roughly 6 to 7 million years ago, okay? Or at least lambda Ori formed about 6 to 7 million years ago. This distribution right here is the dark line, is the distribution of the stars around lambda Ori itself. In other words, around that OB clump. So the story this is telling is that there was a general onset to the star formation 6 to 7 million years ago. The OB stars actually formed rather early in that story. And then there was a rapid rise in star formation, low mass stars, the Colander 69 stars. And then about 1 million years ago, it drops off. Okay? On the other hand, around B30 and B35, that's this lighter line, the formation actually started later, peaked recently, 1 million years ago, and in fact is still going quite strong. And remember, these are the exposed stars. These aren't the embedded stars. All right? The story ends up being the same, but the time scales are different using the other tracks. So to my mind, there's very little evidence here for sequential star formation, but I think there is evidence for the star formation essentially ending roughly 1 million years ago around the OB association while it's still going on in the clouds, which is no surprise because the clouds are still there. Okay. Now, is that what you wanted to know about ages, or now you can ask your question about age? Okay. Now remember, the expansion age for that clump of OB stars is also about 1 million years old. Okay? All right. Yes?
Just to be clear, the ages you're quoting for the massive stars are turn-off
Yes,
ages.
that's correct.
And in some open clusters even, we see a little mismatch between the
Yep.
pre-main sequence turn-on and that turn-off. So I
It's-
just wonder about the scales that make the same.
You're absolutely right, Michael. We're talking about 2 separate systems, and it's not entirely obvious that they are mutually accurate. Which means essentially that I think within the freedom of our uncertainty, you can move these arrows around probably easily 1 million years either way. Easily. Okay, so what kind of story does this all put together? What fits behind this whole story, and what might be a very typical story for a giant molecular cloud, a small one in this case. So essentially, the picture, which is only done very schematically here, is that we start out with a cloud that has 2 density enhancements, which are still currently density enhancements, but the core of the cloud, and most giant molecular clouds do have what in the early days used to be called the cores of the clouds, a more dense place. This is far greater than any scale of clumpiness that Kathy was talking about. We're just talking about broad global structures here. So you can picture a large giant molecular cloud with several density enhancements. And then let me step through the story. So about 10 megayears ago, there was a long chain of molecular gas extending from east to west across the present-day star-forming region, including 3 particularly massive clouds. There's no ring now. That hasn't been formed yet. Numerous OB stars were born in the central cloud, but were rare elsewhere. 1 million years ago, actually, I'm sorry, this is 6 million years ago, let me just be clear. So roughly 6 million years ago, stars formed in the most massive clouds, with the birth rate increasing gradually over many million years. You see that in both distributions. And then the OB stars were born, 12 of them, no, I'm sorry, that's not true, 10 of them were born right there, right smack in the center, right, and only there, nowhere else. Yeah, please.
Is there any reason that low mass stars form at the same time?
They do. In fact, if you go back to that age distribution, let me just step back here. Here. These are the 2 massive stars. This is the formation life history of forming low mass stars. So the low mass star formation happened at roughly the same time and peaked roughly around 1 million years ago. So in other words, this histogram is the age distribution of the current low mass stars. So the very oldest of the current low mass stars were formed when the OB stars were formed. And then there was a progression of increased formation.
And are these low mass stars close to the cluster?
These aren't. The fainter line is the history around the dark clouds B30 and B35. These are in the immediate vicinity of the OB stars. So essentially, they all started forming at the same time in that cluster. Please.
Isn't it that big stars need longer to form and then burn faster than small stars?
Certainly, they burn faster. There's no doubt about that. Theoretically, they take longer to form. Yeah. I'm just showing you an observer's results here, right? Right. It would be very hard to move these stars, even given the comment that Mike made, which was very accurate. It would be very hard to move these ages down to 2 million years. I mean, they're already evolved. We've got them nailed on the tracks. Please.
Couldn't you move the lower mass stars in the other direction by having, for example, accretion? And if you have accreting young stars, then your HR diagram looks quite messy. And if you compare it to a non-accreting HR diagram, you might infer the wrong ages.
That is certainly true. And so what we did was we did the same test with the weak line T-Tauri stars only in those clouds. So I want to be very clear about the story here. There's H-alpha classical T-Tauri stars in both of those clouds, but there also are plenty of non-accreting stars in those clouds as well. It's not just H-alpha stars.
They don't have to be accreting. I mean, this is work by Chris Tao from I can't quite remember the paper, but I think it's just they have to be accreting at some point during the time, and then they will not end up on where you would expect them to be.
Yes.
That would be the other way around. They would be younger than they look.
Right.
So
The systematic effect is in the other direction.
Yeah, so they look younger as they are, therefore they are older.
Yeah, well, it depends on the infall rate. And I actually will take a little issue, Bob, that it might not be that hard to push the O and B stars to the median of your other objects. But actually, if anyone here from Geneva is familiar with the latest in massive star evolution tracks that include convective overshoot and rotation, they would speak more knowledgeably to that.
So you think you can make these stars that are classically 6 million years, you can make them 2 million years?
Well, I certainly don't know, but I remember in this ages meeting a couple of years ago, people saying, oh, look at your lithium edges. That's a much better way to get ages than our turn-off ages. And I almost fell off my chair because I was raised to believe that the gold standard was nuclear turn-off ages.
But for OB stars, it's very tricky. But all I can say is that when we went into the literature and talked to the people that we could talk to, and while they felt very comfortable moving these around by 1 or 2 million years, they had a lot of trouble moving them down to 1 million. Not to say much that for the fact that you've got to get a supernova to go off if you're going to make that ring.
To lay my cards on the table, the reason why I'm troubled more with Kathy and the issue that the clouds would have to last 8 million years and have formed some stars and stay there. If I think clouds don't live that long, I'm a little troubled that they hang around and keep those O stars bound until the gas is blown out 1 million years ago, and then they are able to be free.
So I think the beauty of this from the point of the school is that you're seeing all the issues that we need to deal with as we try to analyze these systems. You've hit them all. That one I wasn't quite expecting because it's not sort of standardly placed into evaluations of ages, whether it be the open Orion or whatever, but you are right, that was suggested at one time, that there's a systematic effect for those stars that had higher accretion rates as compared to lower accretion rates. That, interestingly, goes away, or I'm sorry, lasts after the accretion disk goes away, which makes it very difficult to test. Yeah. Please.
The way I view that histogram, if I just look at the low mass stars, I'd say it's quite a triumphant vindication of premium sequence tracks, because if I'm reading this right, you're indicating that the low mass stars near the OB stars stopped forming when you expect them to.
Yep.
And in the control field, you've got near ones.
Yep.
And I've always been a bit of a skeptic about premium sequence tracks, but that seems to be a very nice consistency thing, that those distributions are definitely different.
Yeah.
And it matches up quantitatively, so I've actually got a positive spin on that.
Which tracks are those then?
Pardon me?
Which tracks are those?
This is D'Antona Mazzatelli, Paula Installer, and Barafidal. All three of them. They all tell the same story with slightly relative different distributions. Okay, let me forge on here. All right, so if you buy those ages, and even qualitatively actually, because what we're really trying to get at is a qualitative evolution of the system, then 6 million years ago or so, the OB stars formed in the clouds, and the low mass stars were forming in the clouds, and certainly low mass stars are still forming today in the B35 and B30, and they aren't forming in the lambda Ori region. Everything I just said is absolutely true, all right? Because I didn't actually pull in any relative timescales in that statement. I would argue, and I'm not alone in this, but that doesn't mean we're right, that 1 million years ago, there was another O star there. Oh, I'm sorry, please.
I'll let you finish.
Okay. That supernova shredding this cloud and essentially creating the ring that we see today. So I mean, this region had a supernova that went off. The blast wave, because these were dense clouds, left, and B35 is not a very massive cloud now, but left behind remnants of these two originally massive clouds, and in the process, now created the ring that we see today. Now to be very, very careful, one of these clouds, I believe it's this one, has the wrong velocity. So this one might have been a primordial cloud long before the ring went off. But the rest of this out here, and the H1 region outside, looks like it's been driven by something, presumably a supernova. Yes?
What about the stellar wind of the central O star in the cavity? Can be dig by the wind instead of another massive star leading to a supernova explosion?
So this is not a domain that I'm expert in, to be honest. So all I could do is ask the people who worked in the field. And their feeling was that the wind could not drive 10 to the 4 solar masses out here. But if you know differently, honestly, I'm not an expert in that field at all.
I just know some simulations of winds of massive stars, and I know that it is possible to dig cavity of different size depending on the density of the ISM and things like that. And the size can be a few tens of parsecs and things like that. It's possible, but I don't know.
I'm glad you mentioned it. And I'm fairly certain you would still need an O star that's more massive than lambda Ori. Lambda Ori is not that massive of an O star.
I don't have the mass of an OA star.
In the OB world, it's not much. You know. Please.
Cannot the ionizing wavefront be responsible for the sweeping out the material?
Again, to the best of my knowledge, no. But if anyone wants to do that computation, please do and let us know tomorrow. I mean, just look at the energetics and see if it works. Nathan?
Yeah, I'm just wondering what the odds are that the stellar remnant would still be in that region. I think the crossing time is on the order of 1 million years. So I don't know what the recoil velocity velocity is and how much greater it is in the velocity dispersion. But if it's on the order of velocity dispersion, it'd be highly likely it's still in the region. And since there's gas all around and there's a stellar remnant, it could be interacting with the gas, or there could be dynamical interactions. Is there any evidence for anything like this?
Not that I know of. And I will say that, you know, the recoil would have to be pretty small to still be in the region.
Right.
Because it's only a couple kilometers per second. So, all right, let me. Oh, please.
What kind of velocities and masses do these clouds have? The ones that are driven by
The total mass in the clouds is about 10 to the fourth in the entire ring. The velocities are very low. I mean, that's why the expansion per se is not at all obvious. It's a face-on cloud. It's very hard to get it from radial velocities. The dispersion around the ring is quite small, a few kilometers per second. Please.
Can you say what is the distance from the galactic center?
From the galactic center? Well, it's Orion. It's about 400 parsecs from us. So 8.5 kiloparsecs? Yeah. Okay. We want to get some alcohol here. Okay. So today we have star formation continuing in the remaining gas, but it ceased in the vicinity of the supernova epicenter. And the future is that I would guess that the star birth in B35 will terminate soon. If you look at B35 carefully, you can see the impact of the winds and other flows past it. You can see it in the shape of it. It's very elongated. And so those who have studied the evolution of B35 suggest it is not much left for the future. But the real point here, and this is really the point for this school, is that A, the story just generated a lot of discussion, which is where we're at in trying to figure out how these regions work. But what is absolutely true, unequivocally, is that there are about 200 stars in this region, 10 OB stars, another roughly 200 low mass stars, which clearly are not globally bound. This is, get rid of the molecular gas, give it a few more million years. There's an OB association, because there's going to be it's going to be a B association as long as lambda Ori hangs around. It's got an entire IMF below it, not adequate to fill the field completely, but it's clearly got low mass stars around it. If later on Gaia looks at this region a million years from now and this gas is gone, it's going to see a larger complex of low mass stars with the same velocities. They may even see what we call streams of stars, like the Ursa Major stream. Ultimately, the OB stars will go away and we'll be left with a low mass stream of stars. The shear of the galaxy will tear it apart, and we have field stars. I think the main point that I want to make here, and this is getting back to the question that you asked, is I really, and I'll say it again, I think the question of whether most stars form in OB associations or in open clusters or in embedded clusters, it's an important question to ask, but the way to go at it, in my opinion, is not to look at them as separate entities, but rather to recognize that all of them are forming in these units of giant molecular clouds, which eventually disperse, leaving behind an unbound ensemble of stars. And I think what we want to do in the next 3 days is to try to figure out how we're going to characterize which of those stars make it into the field, and when they do, in what type of organizational units, and which of those stars end up in bound clusters, which is, of course, the field also, but will maintain that unit of existence. Okay, so if lambda Orionis is representative, star-forming regions are short-lived. Now, Michael may think they're long-lived. They terminate themselves from within, from what they make themselves, and they are not identifiable after roughly 10 megayears. I haven't mentioned at all why the star formation started. I've suggested why it ends, but I haven't suggested why it started. I don't know what sets the rate of it, and I don't know what determines their IMF. I only suggest that it's not universal locally within the giant molecular cloud. And I think we have a lot of interesting discussions over the next 3 days. So there you go. Any questions before we go drink? Yeah.
You mentioned there is ongoing star formation in B30 and B34.
5.
What about the cloud to the lower right? The previous video.
The cloud to the lower right has a different velocity, and there's nothing going on in it, interestingly enough. Yeah. In fact, as far as we can tell, there's very little going on. No, I said that wrong. I'm sorry. Forget I said that. Back. Did you stop the recording? There's nothing going on in any of the clouds of the ring except that one.
Okay.
That one has got an outflow in it, it's got a young star in it, but its velocity suggests that it actually has nothing to do with this system.
Okay.
Thank you. Yeah?
Is there evidence of triggered star formation?
I don't think so, but it all depends on how much you believe those ages. There are certainly, if you believe, even if you believe the ages in a relative sense, there are old, low-mass stars at B30 and B35. That's also where the very youngest stars are, but they aren't all young. And there are older stars there where, if you believe the ages at all, formed more than 1 megayear ago. And so they formed before the shock went by, before anything dynamic happened to those clouds. So even though that's what we were looking for, I don't think there's much evidence for it.
On that point, Bob, do those age histograms have the sort of kernel of the expected errors taken out? You know, if you've got errors
Yeah.
in log L and log T, you'll get a dispersion, even if it's spurious.
The answer to that is no. They are not taken out.
So it could be a little narrower.
Absolutely. Absolutely. Is that true? We took out, no, I'm going to have to read our paper again. It was a decade ago. Because you know, at the same time that Hans and Preibisch were doing that, we were working on it too. We haven't done it at the sophistication level you have. But I think we took out binary dispersions. And I think, I'll have to check. Before I say anything wrong, I'll have to check. We were, you know, when we were doing this, that issue was just starting to come up. Yeah. Please.
About you mentioned this cluster is going to be unbound. So I'm curious about that. There's a paper by Simon
Portuguese White.
So they discriminate cluster bound and association according to the age. If the age larger than the crossing time, it will be bound. So according to this cluster, is already larger than the crossing time. And I will assume that the crossing time before will be even faster than shorter than 1 million years. Yeah. Can you comment on that?
I think everything you just said is correct. So what's your question?
So it's how you draw the conclusion is will be unbound.
Oh, I draw that simply by measuring the velocity dispersion of the system, which is about 2 kilometers per second, doing a census on the mass, and then just doing the virial theorem or any other.
So the dynamical mass larger than the.
You can phrase it that way. The dynamical mass is much larger than the observed mass. I would say the observed mass is much less than what's necessary to keep it bound. But correct. Please.
Just a comment that back of the envelope suggests that the numbers you quoted me for the cloud velocities and masses are consistent with a 10 solar mass main sequence star doing core collapse and 10,000 kilometers per second blast rate. So the numbers are consistent.
I'm pleasantly surprised to hear that. No, I mean that sincerely, since with respect to the dynamics of how this region evolved, I have really relied on those who do those type of calculations. I haven't done it myself, so I'm glad to hear that it hangs together.
And depending, maybe if that mass is 10 solar masses, or maybe it's 20, or whatever is the right number, this duration that you're talking about, I guess there has to be some, right? Because the first star won't go supernova
Exactly.
too fast. It has to take a few million years.
Well, that was the point I was sort of making to you back there. If the supernova went off, they've got to be at least of order 3 or 4 million years old, I was told the other day. All right, thank you. This is going to be a fun 3 days. Now we're getting into it, how these things work.